and today I'm really excited to talk to you all about Thermostat, which is a serviceability tool that helps you identify performance and other hard-to-spot issues in your Java applications. Today we're going to talk about a whole bunch of things. The overall agenda is as follows. I'm going to talk about some of the performance metrics and characteristics that we are interested in obtaining. I'm going to talk about what Thermostat is, how it works. We're going to go through demos, if the demo gods are nice. I'm going to show off some plugins, some of the new features that we have developed in the recent number of years, and finally, some steps that you can take if you want to investigate more or use Thermostat. So let's get started. First of all, what matters to you? As a Java developer, there are a number of things that matter to me. I look at performance, and there are lots of sources where I collect pieces of data from to get the holistic view of what my application's performance is. My Java application doesn't run by itself. It's running in some sort of host, whether that's a single machine, a cluster of machines, containers. And I care about lots of pieces of information. I care about what the OS is. I care about how much CPU I have, what sort of CPU I have, what the memory architecture is, how much memory do I have, what my memory access looks like. And I care about I/O on the machine. What sort of I/O capabilities does my machine have? I also care about a lot of the information that I can get from the JVM. So aside from the entire host, I care about what the CPU usage of my particular application looks like. I care about what the memory access patterns of my application look like, how much memory is my application allocating, how much is it using, how much is it wasting. And really, for Java, that means how the garbage collector is behaving, how often is it collecting garbage. Do I see the sort of patterns that I expect to see in a good application? Is my garbage collector working well, or is it actually fighting the type of application I have? I may also care about how many classes I have loaded. How often am I loading classes? How frequently am I loading classes? How is the size of the classes that I'm loading? I care a lot about the JIT behavior. So Java has a just-in-time optimizing compiler, and I care about how often is it running. Is it doing its job? Is it compiling well? What is it compiling that it shouldn't be? I care a lot about the I/O calls that my application is making. So if my application is doing I/O and it is I/O bound, I care how much I/O it is doing via system calls, how much characters or bytes is it reading, and I want to get a good idea of what the I/O picture of my application looks like. If my application is threaded, I care about what the threads look like. How many threads is it using? Are they running? Are they running in parallel like they're supposed to? Or are they deadlocking or worse, contending on a single shared resource? And then as a Java application, maybe I want to go a little bit further ahead. Maybe I don't care about just getting information. Maybe I want to say, let's make some changes and see how that works. So maybe I want to say, hey, JVM, let's stop, get a heap dump, and we'll analyze and see what the actual memory of my application looks like, how many objects I have, what the sizes of those objects are. Maybe I want to say, OK, this garbage collector isn't behaving very well. What happens if I do a manual garbage collection? What does my application do then? I may think, OK, I might have a deadlock, so we could go ahead and ask the JVM to say, tell me about all the deadlocks you can identify, if there are any. And if I'm really feeling brave, I can say, I'm not getting the information I need. Let me go dynamically modify the code that is executing, insert some other code, get the data I need, and maybe that will give me the information I want. And that's really too many things. They're all different parts of this stack. And really, there's no single tool that correlates and combines that information. We have specialized tools that do one bit or the other bit or another bit. So Thermostat is really our answer to this. Thermostat is a serviceability and monitoring tool for OpenJDK. What that means is it runs side by side with your application. There's no need to modify your application. And it will look at it and identify things from it and present a complete picture to you. Thermostat is targeted towards a number of different scenarios. So I want Thermostat to work really well on my single developer machine. or a cluster, or even a whole bunch of containers that I have. I want thermostat to go up and down the stack. What I mean is I want to look at the application layer and say, I'm running on top of this application server. Maybe I can get information from that. I want to look at the JVM and say, OK, the JVM can tell me these things. I want this too. And maybe even lower down the stack, I want to say, tell me information about the operating system. So it'd be great if we can look at all of those, collect all of that. And thermostat tries to do that as much as it can. We don't just want to collect information. We want to keep it, store it. So maybe not today. Tomorrow you want to come back and say, hey, what happened that day? And what did the I/O look like when I noticed my application is lagging? And obviously, we're all developers, and some of us are sysadmins. Some of us like GUI, some of us like command lines. So thermostat tries to address both those use cases. We have a command line interface where you can script stuff, do command line, automate stuff. And you also have a GUI, so you can click around on things, see pretty charts, and do analysis by looking at things. Obviously, it goes without saying, as a Red Hat project, it is open source. But the more interesting thing is that it is under the same license as OpenJDK. And what that means is if you are OK with using OpenJDK in your production, you have the same sort of licensing concerns, or lack of them, when it comes to running, contributing, and using thermostat. So enough of me talking about what we want it to be. Let's get into the demos. So as I said, thermostat targets a whole bunch of different scenarios and requires different setup for each of them. The ones I'm going to show today are all on my local machine here. So I'm going to do these two sets of commands. The first one is thermostat local. And what that does, it configures and runs everything for my local machine. The second option that I probably won't have time to go into today is the command line. So for that, I will have to do thermostat web storage service and thermostat shell to actually drop into the command line. So let's get started. So here, I just built thermostat from source. It's a fairly recent version. And I'm actually going to run thermostat local from this place. So we see that it's starting up a whole bunch of things. It's starting a server. It's starting data collection bits. And then it's going to launch the GUI. So we can actually look at everything. So this is the thermostat GUI. So on the left side, you can see all the hosts and the VMs that thermostat knows about. And on the right, we get a little bit of an overview. So probably the most interesting thing here is the URL of the project, how to contact us, and reporting bugs. I'll leave those links at the end, so don't worry about it. What we can do is click on a single host and get an overview of everything that is present in that host. So here we see an overview. We see information like what the hardware here is, what the network here is, basics about the software, so what OS am I running here. And we get some charts about how the overall CPU and the memory usage of this host look like. I can click over to this processor tab here and get some detailed statistics on the processors of this host, so I know how much CPU is being used on this host. And I can filter that and limit it by time, so I can see for the last couple of seconds, or minutes rather. I can click on the memory tab here, and that presents me with a complete picture of the memory characteristics of this machine. So I can see things like the total memory available here, how much is free, how much is being used, buffers, and so on. So I can see how my free memory is going down because I'm running things. If this was a NUMA machine, I could get a lot of information about how many different NUMA nodes this machine has and what the access patterns for memory look like on this NUMA node. So we can see hits and misses. And since I only have one NUMA node, it's all hits, obviously. And I have a little cute little notes feature here where I can say things like, this is very important. Don't shut down. And it gets saved, so somebody else looking at it can say, oh, don't shut it down. I can also examine each VM by itself. So actually, let me go to this one, which is more interesting. So we get an overview of the VM again. We see what the process information is, so process ID, user. We see some basic Java information, so the command line, the main class, the VM arguments. But we can also drill down into specifics. So I can see what the CPU usage of this particular VM looks like. So I can see when it started, it was using a whole lot of VM, and now it's much more stable. There's also a built-in profiler. I am not going to show this running because I have something else to show. So I'm going to skip this, but but I want to point out that we do have an instrumenting profiler. So it will modify your code, insert code that measures timings, and we get all the charts out of it. But again, I'll show you something alternate, which is a little cooler, I think. We also have a NUMA tab, obviously not a NUMA machine, so not very useful information. But we also have a very good garbage collection tab. So the garbage collection tab shows you everything you need to know about the garbage collector that is running on this machine. Probably the most important part is you find out what garbage collector it is. And that's not easy to find out by default because there are so many combinations and it's all over the place. But once you know what the garbage collector is, maybe you want to tune it. What can I modify? What options does this garbage collector support? Well, we can click on the little eye icon, and we get a whole set of parameters that this garbage collector uses. So we can see that if we want to set the new size, the maximum size of the new generation using this garbage collector, we can expand that and actually use this exact parameter name. And we even know what this does by looking at the definition here. So maximum size of the new generation in bytes. And we also see that this is computed as a function of new ratio. So maybe we want to adjust that if we were tuning this garbage collector. So going back to it, we see the different generations that the garbage collector is operating on. So we see that the parallel compact collector is running on the old generation. And we see it ran once, and it took, actually, maybe twice, 2 bars here. And it took about 120 milliseconds. OK. We also see the garbage collector running on the new generation. And we see that it has been running more frequently, but has been taking much shorter times. And that's useful to know, because if my application is latency bound, and I'm noticing huge latency spikes, now I know that I probably want to minimize the GC time on my old generation, because normally that's the one that stops the world to collect garbage. So that's one view of memory. We also have another view of memory that sort of drills down and looks at each generation and subregions of that generation. So the new generation is really made out of Eden, Survivor 0, and Survivor 1. And we can see each of that. So this is Eden up here, Survivor 0 here, 1 here, and the older generation, which is old, and the class metaspace down here. We see what the access patterns here are. So we see the very familiar sawtooth allocation pattern, where our application allocates memory, allocates, hits some sort of threshold, the garbage collector kicks in, reduces memory usage, and we sort of do that over and over and over again. We also see so we actually see the memory filling up live right here. And when it fills up, we'll see that the garbage collector kicks in, transfer S1 to S0, and also moves over the new objects from Eden that have survived for a while to S0. So that gives us an idea, do we have the right memory region sizes? Because if Eden is filling up very, 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 very quickly, and the sizes of S0 and S1 are not increasing, we have objects that are very short-lived, so we probably want to increase the size of our new generation. And you get similar information out of the other generations. There's also a heap analyzer. So what that lets us do is that we can trigger a heap dump on demand and then study it to figure out what objects I have in my memory, what their sizes are, how many instances of those objects are around. So I'm going to trigger that one right now and see what happens. So you see a little status here. It's dumping heap. We'll watch it complete. OK, it's done. we get a little pin here that says we took a memory dump at this point. I can double click on it to load it up. Again, it's loading the heap dump, takes a little bit of time. You can see a progress down here. Okay, let me expand this a bit. So here we see a tree map visualization of the heaps. So not only do we collect raw data, we can present it very nicely in a way that makes obvious sense. So just by looking at this chart, for example, we can see that the largest area of memory is taken up by objects of type int array. And that makes sense because I have an application. This is actually doing it on the GUI itself that's running. So we're crunching lots of numbers. Kind of makes sense that we would have int arrays that we're passing around doing processing on. But if we were seeing, for example, lots of strings, it would be a cause for alarm that maybe we're not doing something right. And we can drill down into it. So I see Java util hash map here. I want to see what objects in the util package and its subpackages, how much memory are they taking up. So I'll double click here and zoom down. And we get an idea of, out of Java util, what the different subtypes of this package and subpackages, how much memory do they take up. There's an object browser, so I can use it to search for types. So I can say, show me all the weak hash maps in this VM. Oops. Yeah, there you go. Hash maps. And then we get a whole list of all the instances that we know about. What's more is that because we have selected referrers, we can expand each of these and get an idea of what other objects are referring to this one. So for example, we think we have some objects that are not being garbage collected. That means someone has a reference to it. How do we find it? Well, let's find the object here. Let's find everything that it refers to, see that it makes sense. If I click on an object, I'll get a little more information about it down here. We'll see things like the object ID, the type, the size, and where it's allocated. We have another view for it. So the heap tree map showed the total size. We can also look at instances and search by names. So I want to see how many Java lang.strings I have. So I'll see that I have about 1,000 instances, and okay, 26K, not too bad. If I hop over to the I/O tab, I'll see what the I/O access patterns of this JVM look like. So there's a bunch of information here. Let me try and simplify it first. So we see two charts, one that talks about how many characters it has read, which is the red line, and the characters written, which is the blue line. And we can also compare that to syscalls. So we can find out how many read system calls have been done and how many write system calls have been done. So if we do a comparison, we can see how many characters are we reading per system call. And if we're reading very, very few characters, that means we're probably not buffering correctly, and we need to look at that. There's also the threads tab. So this gives us an overview of everything we want to find out about threads. So this chart up here shows the total number of threads in the system. And these are the number of daemon threads down here. And that's basically the number. So the difference between the two is the number of non-daemon threads. That's cool. Not very useful, but that's cool. What's more interesting is the timeline view. So because with Thermostat, we don't want to perturb the machine that we're monitoring too much, there are lots of things that are off by default. So we actually have to go in and say, OK, I'm interested in this piece of information. Go ahead, touch my VM. I don't mind. Get me that information that I really want. So we're going to do that here. I'm going to click on the little record icon here. And then Thermostat is going to go ahead, instrument the VM, in this case itself, and show us a timeline of every single thread that is running. I'm going to zoom in a bit to see things a little better. And now we see a timeline of each thread. So this tells us how many threads there are and what state they're in, which is really cool because if I have a thread that I thought should be running all the time and it says it's not running, something's wrong. What's really cool is that we can see different colors here, for example, and they tell us the different state the thread is in. So we know that red means this is blocked, and orange means it's waiting, which is cool, and the blue ones are running. That makes sense if everything is blocked. Or the more interesting use case is when you have two threads that you thought were supposed to be concurrent, but every time one is running, the other is blocked, and every time the other is running, the first one is blocked. That means your parallel threads are really not concurrent and are actually waiting on some sort of shared resource that we need to look at and fix. We can also get some statistics about the number of locks in the VM. So how much is it locking? How much contention is there? Or how many spins there are, deflations, lots of details if you are into that sort of intricate locking and synchronization mechanisms. There's a stack trace profiler. I'm going to jump on it, jump over it now, come back to it later. There's a compiler tab, so that shows us statistics about the JIT compiler. So everything we possibly can get from the VM. So how many times has it compiled? How many times has it said, nope, don't want to compile? How many times has it said, sorry, how much time has it taken to compile the code that it has compiled? And what is the size of the code that it is compiling? And we see that over time too. So let's hide these two so that will make it more interesting. So we see the total number of compiles that have happened in this JVM, and we see there we've done like 15,000 compiles. And we see how that changes over time. So once you say you have a stable server application that has gone past the initial startup phase and is running continuously, you don't want to see any more compiles. And if they're happening, maybe that's worth investigating. Why is the JIT compiling methods that it really shouldn't be ever? There's also the classes tab, and that shows us how many classes we have loaded, what their sizes are, how many classes we have unloaded, and what their sizes are. In normal Java applications, we expect classes to be loaded and never unloaded. But if you're using an application server or some sort of OSGI, then unloading matters too. And you want to be very careful that stuff you're using doesn't get unloaded and reloaded back, because that's a problem. Why do that? There's a very cool Byteman tab here. I'm going to skip over it again. We'll come back to it, don't worry. Finally, or well, second finally, I guess, the notifications tab. And this shows us all the JMX notifications events that have happened in our VM. Again, because this is JMX and it sort of impacts the performance of our VM, we don't enable this by default. So again, you can click on the play icon here, get that data and study it. And we have the notes again, so we can say things like important VM, demo it, cool. And it stays around if you come back to it. So let's exit that. Going back to the slides. So we've seen what Thermostat looks like, how to use it. I want to go back a little bit and talk about the architecture of Thermostat. So Thermostat consists of three main components. So the first one are the agents, which are the little boxes here. So that's a Thermostat agent. Each agent runs inside a host, which could be a developer machine, it could be a container, it could be a cluster, but just one single item there. And each agent connects to one or multiple JVMs. So this particular agent, for example, connects to two JVMs that are running inside a single host. This agent connects to three JVMs that are inside a single host. What the agents do is that they connect to everything in their environment, start pulling it for data, collecting it, and sending it over to storage. So the storage piece of Thermostat acts as our database. It records everything, keeps everything, so we can do analysis, we can visualize it, and really do anything we want with it. The clients actually pull data from storage and do all the fancy analysis and charting that we have seen. There is a sort of back channel from the clients to the agent, and that's required because Thermostat isn't just a read-only thing. We actually go and modify the JVM when we need to so we can get more data out of it. So there's a command channel for doing this side communication. And well, our storage isn't exactly just a simple storage. It's a security layer that keeps the storage behind it. And what that lets us do is make sure all the connections are secure. And no agent can fake being another agent, and we can be sure that clients can only read data that they're authorized to. So you can run this in an environment where you don't fully trust everything and not worry too much about data being leaked where it shouldn't be. So that's the core of Thermostat. Let me get some water. Now I want to touch a little bit about plugins. So what I showed was Thermostat working out of the box. And that's great, because we do all this sort of data that you wouldn't find out about otherwise. But really, sometimes when you're running an application, you don't care about any of those metrics. You want to use as a metric the single task that the application is doing. So if you're sending email and you have an email server and the only job it has to do is send emails, that's your metric. That's what you want to monitor. Nothing else that I talked about, obviously. And one major way we let you do that is through plugins. So you can write plugins for Thermostat, and plugins will modify our agents or our clients. And with this, you can collect your information, record it, analyze it, display it. Basically fits right in. This lets you support your own custom applications, their custom metrics, integrate any tools that you have in-house. We have a documented and stable API for plugins, so you don't have to worry too much about things breaking. When there are changes, they're published as part of new releases. So, actually, before I move on, I have a demo for this. I keep on forgetting. So let me find the plugins demos. Oops. So before I go on, I'm going to delete all my existing stories so we start with a brand new thing. And sorry, increase the font size. So I have a custom application. As I said, let's pretend it sends out emails. It doesn't. I don't want to spam people. So I'm going to run this. So it's going to build a program and run it. And now I have a Java application that I developed running. And it's collecting something. I also have a plugin I wrote. So this is a custom plugin. So I built it before, and I'm going to install it into a Thermostat installation. And then when I do Thermostat local again, got to be in the right directory. So when I do Thermostat local again, it's going to run Thermostat with the plugin loaded, and we'll see what that does in a minute. Cool, so it's up. Now in this list, we see that in addition to the 3 Java programs that we saw, GUI, local, and command channel, we also have a new program, which is what I just wrote. And if I hop over here, right after notes, there's a new tab that's now available. Cool, eh? And I can open it up. And now in this tab, we see that Thermostat is actually collecting the metrics from my custom application. The agents are collecting it. It's being stored in the database. The clients are displaying it. So I've just integrated an external tool into Thermostat. And just like this, you can integrate anything and collect anything. And you get the same set of advantages that our native components have. So this will actually work offline. So if I kill the application, I still have this data. I can still look at it. So let's talk about some of the newer features that we have done in the last couple of months. The first feature that I want to talk about isn't that recent, but we've been improving it quite a bit. I'm going to have to be honest. I cannot do justice to this in the little time I have. If you want the entire thing, Andrew Dan, who's the developer for Byteman, did a talk on this last summit. It's a less polished version of the same thing, but you'll get the same idea. So if you want, you can Google for monitoring application-specific behavior using Thermostat and Byteman to get an idea of all the cool things that this can do. I'm going to do a really, really brief thing. So let me first touch on Byteman. So for those of you who are not familiar with Byteman, Byteman is a bytecode instrumentation tool, a dynamic tool at runtime. So what it does is you take your Java application, it's running. You can take Byteman and say, hey, that application that's running here, I want to modify it. So Byteman will inject bytecode, tweak the application that's running, and make it do something else. And then later on, you can say, no, I don't want that, remove my changes, and they're gone. So this gives you a lot of powers. You can do some crazy things. One really amazing thing that you can do, maybe it's not a sane idea, is if you have a vulnerability, you can say, that little code that has a vulnerability, let's use Byteman to modify this. So when we hit that error condition, don't do that vulnerable code, do this new thing. So no more vulnerabilities. We can also use that for fault injection during unit tests. So if you have a unit test that is exercising an API, chances are that API might never fail. So if you're doing file I/O, for example, you're never going to hit an exception. Your unit tests are always going to pass. How do you verify that your unit test is working correctly? You use Byteman to say, when you're using that file API, don't do the normal thing, throw an exception. And now your unit tests can actually test for that exception. Well, that's all great. What we can do using Thermostat is even more fancy. We can say, here's my application running. Use Byteman to inject custom code in the VM, make it get metrics that weren't implemented there, get those metrics out, use it, and display it. So let's see how that works. I'm going to stop what I was running here before. Yep, stop everything. So again, I'm going to clean my old data just to make sure nothing crazy sticks around. That's that, and I'm going to run the Byteman demo. Make run to start. So this demo is actually based on a customer case that we got where they were observing behavior that didn't match their expectations. They had a slow thing and a fast thing that weren't behaving like they expected it to. But their application is written, we can't really do anything with it, but we want to get data out of it, data that isn't available right now. So what we ended up doing is using Thermostat for this. Oops, wow. I think something bad happened. Let's see if this works. OK, we're back up. So now we have this demo program that's running. What I am going to do is to use Byteman, instrument these slow and fast operations, ask it to send me metrics that are not available. So first I'm going to go over to the Byteman tab. Maybe make this a little bigger. OK, there you go. And I'm going to load up a Byteman rule. So a Byteman rule really describes what to do. And I do not have time to go into this, but what this little script is saying is, in this class, in this method, when that happens, do this. And the do this part is very generic. For Thermostat, our do this is send metrics back. So we're going to inject this into the running VM. So now this demo application was modified without changing any code to do something new. So I'm going to hit the fast button. And now it's doing what it normally does. Cool. But if we go over to Thermostat, we see we're actually getting metrics out from it. So we just got metrics from an application that wasn't designed for this. And OK, so fast is done. Let's run slow. And again, we're getting more metrics. That's cool. But raw data, that's not very useful. Let's graph this out. That's going to be much more interesting. So I can pick my x and y axes and say, OK, I want timestamps. And of the many metrics we are transferring, or rather getting from this application, I want to plot this thing called transition. And that's a lot of information mixed. So let me try and filter it further. So I'm going to say, OK, give me a marker of work. So this is something specific to this application. You can use whatever marker you want. This is entirely based on the Byteman scripts that you use. So in this case, we were just able to plot how long a method was called and how it returned. So this is when the method was called. It returned, did something else, called again. That's how long it ran, and returned. We just plotted its state transition diagram for an application that wasn't designed for this. And we can do some more interesting stuff. So we can plot things like, how, based on the input, how long did it take? And that. Oops. Sorry, ID. Always mix this up. So yeah, based on this ID, we can see based on the slow, fast, which ones, how long did they take, and we can observe data that there's no way we had before. Another cool new feature I want to show off is the stack trace profiler. So Thermostat has had a profiler for a while. What is new is the stack trace profiler. So I'm going to hop over to the Threads tab and fire this up. Again, it's one of those things that's fairly invasive, so we try not to do it by default. So I'm going to go and start it. And here we have the amazing flame graphs. So for those of you not familiar with flame graphs, the x-axis tells us how long something takes, and the y-axis is the call stack. So we're saying that the total time is here, and this is how much time this call stack takes. This is how much time this call stack takes. And we see that it's getting smaller and smaller because we're showing the time that one method takes in terms of how long it takes when it calls the other method. So this little here, that's all the time it takes. There's nothing it calls. Going back. Ooh, so how many of you have actually heard of Shenandoah? Oh, dang, OK, we should talk about this more. So Shenandoah is a new garbage collector that we're working on in OpenJDK. The goal here is ultra-low pause times. So for a little bit of performance loss, you get very, very low predictable pause times. I'm going to show this in action, and then I'm going to show what Thermostat can use this, or how it can use this. So let's keep this running. Exit that. I am going to start. Oops. Doesn't matter. So I'm going to fire up my demo again and Shenandoah demo. So Shenandoah is a garbage collector. The goal is it uses several advanced techniques that I possibly can't explain in like the couple minutes I have. But what it does is that it uses a number of tricks to say, I want to make sure that my garbage collector runs for a very, very, very small time in a way that blocks your application. And when you're developing a garbage collector, or even when you're using it, sometimes you want to see, OK, what's going on? How's this working? Thermostat has a Shenandoah tab where we can see the garbage collector actually working. So you see this is the entire memory. The green stuff is the regions of memory where objects are fully live. And the blue stuff here is objects that are fully live but recently allocated. So just by looking at it, you know my entire memory is being filled up with objects that were just recently allocated. Shenandoah is actually not a good fit for this workload now because we want a generational garbage collector, something where we can put lots of new objects in. But for another case, you can see, oh, my access patterns, my garbage collection patterns fit here perfectly, and Shenandoah is definitely what I want to use. I'm going to stop this now. Go back here. OK. Oh, another cool thing. First, I'm going to start a demo, then describe this, because this is going to be tricky otherwise. So I'm going to do a problem. So I'm going to run an application. I don't know. It's broken. I don't know what the problem is. And I am going to run a custom build of thermostat. So this feature that I'm showing is not in the main repository yet. It's one of the side development branches. So again, clear all data to make sure I don't trip over my configuration involving security. And we're waiting again for it to start. Oh, there we go. So now we have a little program. Let's pretend you didn't read the name of the class. I'm going to hide it. So this is a really cool new feature that we have been working on recently. What it does is, well, first, there's a little status icon here. This icon means it's working. We'll see why. So what this feature is doing is looking at the memory allocation and the memory usage patterns of my application. Again, this is in development, so we're seeing some raw data that it's using. So it's doing some charts and its computation. What it's going to do is look at the memory trend. So how much are we allocating? How much are we using? Is it making sense, or does it look kind of shady? And again, it's doing more candlestick charts to see, yeah, memory should be that high or not that high. And if we wait just a little bit, it's going to figure out if this memory allocation pattern is a good thing or a bad thing. And then it's going to tell us. So it's doing an analysis of all the data, all the historical data, which is why it's taking some time. It needs a certain bunch of data to get started. But when you're running this against production, you have lots of servers that have been running for a while. So you're not going to have this problem of waiting for data so much. And, oh, there you go. OK, so now we get a result of all this automatic analysis. Thermostat gave us a thumbs down. This application has a memory problem. We didn't look at anything. We ran thermostat, gave it a little bit of time, and it said, memory problem, go debug, fix. No looking at charts, no searching for data, nothing. Again, this is in development, so this is something we're going to improve a bit. Oh, and I have no way to show this, but we have a Windows port in progress. So you might have heard that Red Hat recently started supporting OpenJDK on Windows for development, and so we're porting over our tool to Windows as well. So this is all thermostat. These are some of the amazing features that it has. What do you do next? Well, there's a little bit of history that I am going to skip because I'm running out of time. But the point is, thermostat has been in development for a while. We have standard API versioning. So yes, we break API. Yes, we're careful about it. So if you want bug fixes, we put in 1.6. Doesn't break API. 2.0 will break API. But we'll announce that way ahead. So some of the things that we're looking to do is integrate with more tools. So you saw how we integrated with things like Byteman. We want to integrate with more tools across more layers of the stack. So maybe something like System Tab for even lower level analysis. We have some automated machine learning and detection. And we want to improve that to cover more areas. One big thing that we like to work on is better support for cloud architectures and microservices. We already have an architecture that we feel fits in pretty comfortably. What we want to do is to do some sort of UI improvements, maybe add some sort of web UI that works better in the scenarios where you want to run it, say in OpenShift. Oh, and this is how you use thermostat. So thermostat is part of RHEL 6 and 7 through the Red Hat Software Collections product. It's also available in Fedora. Or if you're adventurous, you can go download the sources, build it yourself, and run it yourself. We accept patches if you have any. I'll take it. So yeah, starting point is our website, ist.classpath.org/thermostat. And it has pointers to mailing list, IRC, bug tracker. Yes, we use IRC. We are open source. We're bug tracker. And if you want to send in contributions or ideas, we're accepting features. send us bugs our way, sure. Code contributions are even more awesome. So just to recap, I went over why we want Thermostat, what it is, how it works, some cool things like plugins and new features, and what you want to do if you're interested in finding out more. Well, I want to thank you for attending my talk. I hope you all learned something very educational. And if you have any questions, I'd be happy to take them now. So the question was, how does Thermostat communicate with the JVM? And it does that through various different mechanisms based on what tooling we're trying to use. Actually, I'm going to put this back up. So for some levels, we use the attach API to insert native agents or Java agents that are then changing various things, and we get that information. For things like JMX notifications, we're doing a standard JMX attach. Get events that way. So it really depends on. So Thermostat is more of a, we have all these awesome tools and features. Let's get them in a way that's nice, usable. So depending on what we're doing, we'll use the appropriate features. So the question was, are we targeting this towards production systems? And the answer is absolutely. So by default, we have a very low overhead on the program that we're profiling. Anything that might impact runtime significantly is off by default. So things like profiling, JMX, you actually have to go in and say, yeah, do this. So by default, it should have a very, very low overhead on your application. So that's not, so the question was, do we support connecting to remote VMs? And that's not really the architecture we're going for. We are assuming that everywhere where a JVM is, we're going to have a Thermostat agent. OK, so again, I guess this goes back to the earlier question, which is, how is Thermostat collecting data? And we do it through various different mechanisms, depending on what data we're collecting. So to give an example, if you want data about hardware or the kernel, maybe we'll look in /proc. If we are interested in data that is part of the JVM stat, hsperf. So basically, when the JVM is running, it's writing some data all the time, which is called hsperf. So for that, we just go to that file using standard APIs, read that file, and we know what the JVM is behaving like. For certain other things, we use, again, appropriate mechanisms. So we have a Java agent, and what we do is use the attach mechanism to connect to that Java agent, get that information. So it really depends on what we're trying to do. There's no general way where we say, OK, we'll only use this way to connect to our application. So the question is, do we have any plans to integrate with centralized logging? Not at this time. But I mean, I've heard people, they're brainstorming, saying, OK, maybe if we connect this to PCP, send and receive data from there. It's theoretical at this point. If you send in a patch, I will probably accept it. But it's not something we're working on. I think we're running out of time. So if you don't mind, I'm going to go outside, and I'll be happy to answer any questions you have. But I'm just going to clean up here. Thank you. Thank you.